All right, so I wanted to take a look at a review example to begin with today. And so we're going to show that the integral is independent of path. And evaluate. And so we're going to look at this integral in differential form. So we're going to have 2x e to the minus y dx plus 2y minus x squared e to the minus y dy. And so if this integral is written in differential form, but if we wrote it in the form f dot dr over c, the f would be, in this case, equal to 2x e to the minus y, and then 2y minus x squared e to the minus y, like that. And in this case, I just realized I forgot to write the last part of the problem, where C is any path from 1, 0 to 2, 1. All right. And so if this is our vector field and this is M and this is N, one way to show that the integral is independent of paths is to show that the vector field is a conservative vector field. So if the vector field is conservative, then that will tell us that the integral is independent of path. And so what would be a way that I can show that this vector field is conservative? If this is M and this is N, what do I need to show here?
That my equals nx.
Awesome. Yeah. So if we have my is going to be equal to minus 2x e to the minus y. And x, well, the derivative of the 2y is 0. So we're just going to have minus 2x e to the minus y. So my is equal to nx. And that means that f is a conservative vector field. So the integral is independent of path. All right, so the next thing we do, once we know it's a conservative vector field, the next thing we want to do is we want to find a potential function. So we want to find a potential function, and so then that makes it easy to evaluate the line integral using the fundamental theorem for line integrals. All right, so since f is conservative, that implies there exists f such that the gradient of f is equal to f. And remember, we call this little f, we call that a potential function. We call that a potential function. And so remember that the gradient of f is the vector where the first component is fx and the second component is fy, and that's equal to this vector field. So this implies that fx has to be equal to what? This one, 2x e to the minus y. And so to find f, we just need to integrate this. We're going to integrate with respect to x. So when we integrate with respect to x, we're going to get f of x, y is equal to what?
X squared e to the negative y plus a constant.
X squared e to the negative y. And that constant is going to look like some function of y. So we'll just call that h of y. Because if I differentiate this with respect to x, I would get 0 for this one. All right, so now we also know that fy, which is going to be equal to minus x squared e to the minus y plus h prime of y, has to be equal to your n component here. So this is equal to 2y minus x squared e to the minus y. So notice that we have a minus x squared e to the minus y on both sides. So that means that we can cancel those by just adding x squared e to the minus y to both sides. And so what that leaves me is I have h prime of y is equal to 2y. And that means that h of y is going to be equal to y squared plus a constant. And for simplicity, we don't need to have plus the constant because we're just going to be doing subtraction. And so that constant would cancel. So we're just going to take c equal to 0. And so what that means is that my f of x comma y is equal to x squared e to the minus y plus y squared. And so what that means is that if I look at my integral, and my integral was 2x so this is going to be equal to the integral. It's independent of path. So for any path from 1, 0 to 2, 1, we're always going to get the same answer. And then this is just going to be the gradient of the x squared e to the minus y plus y squared. And I think you could see that if you took the gradient of this, you would end up with, the vector 2x e to the minus y for the first component, and then you'd have 2y minus x squared e to the negative y for the second component. So these, in fact, would work out. And then by the fundamental theorem of line integrals, the integral just gets rid of the gradient. So we're going to have the x squared e to the negative y plus y squared. And we're going to go from 1, 0 to 2, 1. All right, so let's put these in, subtract, see what we get. So we're going to have 2 squared e to the negative 1 plus 1 squared. And we're going to minus this. We're going to be minusing 1 squared times e to the 0 plus 0 squared. And so what this is going to give me is I'll have 4 over e plus 1 minus 1, and that's equal to 4 over e. I get that. Questions on this part? All right, so I would like to work this integral in a different way. So the integral is independent of path. And so what that means is that any path from the point 1, 0 to 2, 1 should give me the same answer. So if I look at the 1 point was 1, 0, so it's right here. So that's 1, 0. And then the other point was 2, 1. And so we have that. And so there's lots of different paths that I could pick. I could pick one like that goes like that. So I could let that be a path. Or I could maybe have a path like C1 that goes to 2, 0. And then another path, C2, that goes straight up. And so it doesn't matter which path I pick because the integral is independent of path. That means that I should get the same answer if I parameterize for this curve or I parameterize for this one followed by that one. So remember that a path is a piecewise smooth curve. So even though this isn't smooth, it's piecewise smooth. So the pieces are smooth. So the easier way to do this one is to do the horizontal one followed by the vertical one, because that's going to make the integral easier. So let's see what happens. So what I'm going to do is I'm going to let C equal, so let's call this C3 just so that it doesn't get confusing. This was maybe C3, the straight path. So let's C equal C1 union C2. So what that means is that I'm going to go from 1, 0 to 2, 0 along the x-axis, and then I'm going to go straight up from 2, 0 to 2, 1, like that. So let's let C equal this path. Then if we look at the integral over C of 2x e to the minus y dx plus 2y minus x squared e to the minus y dy, that's going to be equal to the integral over C1 plus the integral over C2. Now, let's see how we can parameterize these. So for C1, we're going to have x is equal to x and y is equal to 0. And then the x is going to go from 1 to 2. And in this case, we're going to have the dx is equal to dx, but since y is 0, dy is equal to 0. And so that's going to simplify what we have here. And then for our C2 in this case, for that one, we're going to have x is equal to 2. Sorry, we're going to have x is equal to 2. And then y is equal to y. And so because x is a constant, we're going to have dx is equal to 0 and dy is equal to dy. And in this case, the y is going to go from 0 to 1. All right, so let's plug in and see what we get. So for the first one, we're going to end up with this. So we're going to have the integral from 1 to 2. We're going to have 2x e to the minus 0 times dx plus 2 times 0 minus x squared e to the 0, and then the dy is 0. All of this is times 0. All right, and then for the other one, for the C2, we're going to have the integral from 0 to 1, and then we'll have 2 times 2 e to the minus y, all times 0, plus 2y minus 4 e to the minus y dy. So we have all that. So since all this part is multiplied by 0, this part is gone, and this part is gone. So what that leaves me with is just the 2x. So I'm going to have the integral from 1 to 2 of 2x. And then with this part, I'm going to have the integral from 0 to 1 of 2y minus 4e to the minus y dy. And remember, even though I picked a particular path, it's independent of path. So I'm just picking one to make the calculation simpler. So what this will give me is I'm going to have x squared from 1 to 2 plus y squared, and then plus 4e to the minus y, and we're going from 0 to 1. All right, so if I put these values in, what I'm going to have is I'll have 4 minus 1 plus 1 plus 4 e to the minus 1. And then I'm going to be minusing here 0 squared plus 4 times e to the 0. And so what that will give me is I'm going to have 4 plus 4 over e, and then I'm going to be minusing 4. So I get, again, 4 over e. So it comes out. So we could also do this. We could also do the path right here where we integrate along that line. It's going to be a much harder integral where we're going to have to do integration by parts several times to get it to go through. So because we did these horizontal and vertical line segments, it was easier like this. And since it's going to come out the same for any path, we might as well take one where the calculation will be easier. Of course, the easiest way to do it, most likely, is just to use, to find the potential function and use the fundamental theorem for line integrals rather than calculate it directly. Questions on that? All right, so I want to get started with Green's theorem. So we're going to talk about Green's theorem today. And let's first of all look at the statement of Green's theorem. So this is section 16.4 here. So we're going to let R be a simply connected plane region. And remember, that means that no holes, whose boundary is a simple, closed, piecewise smooth curve C oriented counterclockwise. Then if P of xy and Q of xy have continuous first partials on some open region containing R, then our line integral is equal to this double integral of qx minus py dA. So what this Green's theorem does is it turns a line integral over a closed curve into a chapter 15 double integral, where we're just integrating over this region R, the qx minus py dA. And so one thing to remember, a lot of this may seem kind of technical or whatever, but the thing to keep in mind is that Green's theorem will only work when we have a closed curve. So the other theorems that we had, like the fundamental theorem of line integrals and just working with line integrals before, there we had sometimes the curve was closed, sometimes it wasn't. But Green's theorem is a nice, usually it's a shortcut, will make your life easier, but it has to be a closed curve. And that's why we have this notation here. You notice in this integral, we have this little circle. And what that indicates is that it's a closed curve. So it's a line integral that's a closed curve. And that's why we usually put this little symbol here when we're doing Green's theorem. All right, so what we want to do is we want to get some idea of why Green's theorem works. And so for simplicity, we're going to assume that R is both a type 1 and type 2 region. And so that makes it a little bit easier to argue it out. And so what we want to do is we want to show that this line integral is equal to this double integral. And so if we can show that the line integral over C of just P is equal to this double integral of negative Py dA, and also we can show that the line integral over C of Q of xy dy is equal to this double integral with Q of x, then it follows that the sum will be equal to the sum of these guys, which is equal to what we're looking for here. All right, so we just have to do these two parts. So we have to show that this line integral is equal to minus Py, that double integral of negative Py over R. And we have to show that the line integral of Q is equal to the double integral of Qx over R. All right, so what we're going to do is we're going to look at this a couple of ways. So let's focus in on this part here. So we've got this curve, this region, and remember we have to traverse it in a counterclockwise way. So the Green's theorem, it has to be counterclockwise. And so we're going to call this curve here y is equal to g1 of x when a is less than or equal to x is less than or equal to b. And then we're also going to have the inverse function, x is going to be the h1 of y, where y is going from c to d. Now here, you have the C2. And so we have this curve here is going to be y equal to g2 of x, the curve that has this graph here. And a is going from a to b. And then we're going to have x is equal to h2 of y, where y goes from c to d. And that describes this curve. All right, so let's take a look at let me zoom out just a little bit here, sorry. Okay, so we're going to have the C1. We're going to let x equal t and y equals g1 of t. T is going to go from a to b. And then in this case, we need to take minus C2. So minus C2 is going to go the opposite way. C2 is going this way to continue in the counterclockwise. So minus C2, we're going to take x equal to t and y equal to g2 of t, t going from a to b. All right, so then if we look at the integral of p over c, that's going to be equal to, c remembers the union of c1 and c2. So it's going to be equal to the sum of these two line integrals. Now, C2 remember that if we make it the line integral with the opposite orientation, if we change the orientation on the path, so we make it minus C2, then we have to put a minus out in front. So this becomes the integral of P over C1 minus the integral of P over minus C2, where minus C2 is shown here. All right, so now what we can do is we can rewrite our integrals with the parameterizations. So we're going to have x, remember, is t in C1, and y is g1 of t, and the t is going to go from a to b. And then if we look at minus C2, we're going to have x is t, and then y is g2 of t, and t goes from a to b. Now, what we can do is we can factor out a minus. So if we factor out a minus, and then we put this p, where we put it in that form before we evaluated the different limits of integration, then we have this. So what we're ready to do here is we're going to put the y equal to g of t in the top, and we'll subtract, we'll take that, and then we'll subtract putting y equal to g1 of t at the bottom. And when we subtract that and distribute the minus, we'd be right back to here. Now, if we integrate the py dy, that's going to give us p, and so that would take us right back to here. So we can write this as this double integral. Now at this point, t is what we call a dummy variable. It doesn't matter whether we call it t or x. So we can rename t x at this point. So we have this. And then what this means is that we're basically integrating over a region. So if we swip this out with vertical line segments, we would have r there. So this is equal to minus the integral, the double integral of py over r, right? So that's our first goal. All right, so let's take a look at the second part. So now we're gonna use the function, the x is a function of y. So we're gonna have the integral of q over c is equal to c1 plus c2. And in this case, we can say that c1, we're gonna have y is equal to t, and x is equal to h of t, and t is gonna go from c to d. And then minus c2, you're gonna let y equal t, and x is equal to h2 of t, and t is going to go from c to d. And so again, what we can do is we can make this a minus c2, and so then we're going to have this, putting in our parameters and then our functions of t. And so then we can combine these into one integral here. And then we can write this as q of xt. And then we have the limits here. So if we put in these limits then and subtract, we would get right back to here. And so this is the same thing as qx dx, because when you integrate the qx with respect to x, you just get q. So that would put you right back to here. And at this point, when we get to this level, t is considered a dummy variable, so we can replace the t with something else. We'll replace it with y. And so y is going to go from c to d. And this gives you qx over r. So in this case, if we swept our region out with the horizontal line segments, the horizontal line segments would go from x equal to h2 of y to x equals to h1 of y all the way through. And so we're talking about integrating over r. And so the result follows because now we have the line integral of p equals minus the double integral of py over r, and the line integral of q equals the double integral of qx over r. And so adding those up, we have the result of Green's theorem. Now, one thing to point out, later on, we're going to be talking more about the curl and the divergence of a vector field. And so this integral, we can think of this as like, this is basically an integral that we can use to calculate work, the work being circulation of particles around the curve. So we call this the circulation on C. And if we look at the Qx minus Py, that's what we call the circulation density. So I know you're used to talking about mass density, but there's other kinds of densities that you can look at. And so this is circulation density, where C is a closed curve containing R. And then sometimes we use the flux form of Green's theorem. Our book doesn't talk about this too much, but we may talk about it a little bit later. And so the net flux, thinking about that as like maybe droplets of water that are inside the region contained with the boundary curve and maybe flowing out of the region across the boundary curve. And so the flux across that boundary curve would be equal to the flux density, integrating the flux density over R. And this later on, we're going to call this flux density is what we'll call the divergence of the two-dimensional vector field. And this is the curl of the two-dimensional vector field, the circulation density. And so there's a couple properties that we'll talk more about later, but I'm going to point out now. So if the vector field is PQ, then the curl of F is equal to QX minus PY, and the divergence of F is PX plus QY. So for small rectangles Rij with boundary curve Cij, counterclockwise orientation, if we have a point inside the rectangle, then the curl of F multiplied by the area of your rectangle is equal to the circulation around the boundary of that rectangle. So this curl multiplied by the area gives you the circulation around the boundary curve of the region. And then the divergence of F multiplied by the area of your rectangle gives you the net flux across the boundary. So if that were positive, then you would have, if we're talking about droplets of water, you'd have like more going out of the boundary curve from the region. So we'll talk more about curl and divergence later on when we cover that section. So what we want to do is we want to look at some examples of using Green's theorem. And I think you'll see that it's a nice shortcut when we have a closed curve to work with. So let's take a look at our first example here. And so we're going to use Green's theorem to evaluate And so we're going to have this nice triangular path here. All right, and so we want to evaluate this line integral over this triangular path. And so if we had to do this normally, we would have to have one parameterization for this curve along the x-axis, another one for this vertical segment, and then a third one for this last segment. So we would have to, and then we'd have to evaluate the line integral on each of those segments. and then add it up. So it would be kind of a pain in the neck to do that because there's 3 individual segments. But with Green's theorem, we're going to see that it's much easier. So we're going to have the x squared y dx. And we don't necessarily have to write this little thing. That just indicates that it has to be a closed curve, but we don't have to necessarily always write that. And so what I like to do when I'm working with Green's theorem is I call this one P, and this is Q. And so by Green's theorem, this is going to be the double integral over R. We're going to have Qx minus Py. So Qx is going to be equal to 1. And we're going to subtract Py, which is x squared. And then we're going to have just dA. All right. So now we have this nice double integral. We're back in chapter 15 over this nice region. You can do it type 1 or type 2. It's pretty easy, type 1. So we have y is equal to 2x here, is this curve. And so it's easy to integrate it using sweeping out the region with these vertical line segments. So if we do this double integral, if we do it as a type 1, we're going to have 1 minus x squared dy and then dx. And so how will the y go in this case? So y is going to go from 0 up to
2x.
2x. And then we're going to take those vertical line segments starting at 0 and going all the way to
1.
1. And so we just have this to evaluate. And so what we're going to have is we'll have the integral from 0 to 1. And then we'll have 1 minus x squared, that's a constant, times y. And then 0 to 2x. So I mean a constant with respect to y, because we're integrating with respect to y. And then we're going to integrate that with respect to x. So if we plug in 0, we're just going to get 0 there. So let's plug in the 2x. So we'll have the integral from 0 to 1 of 1 minus x squared times 2x dx. And so we have the integral from 0 to 1 of 2x minus 2x cubed. So we can integrate that. So we're going to get x squared and then minus 1/2 x to the 4th from 0 to 1. And so it's equal to 0 when x is 0. But at 1, we're going to get 1 squared minus 1/2 of 1 to the 4th. And so we just get 1 minus 1/2, which is equal to 1/2. And so using Green's theorem is a pretty straightforward problem, much more difficult if we have to parameterize around each of these segments and then add up the 3 line integrals for each part. Questions on that example? So you can think of Green's theorem as kind of like a shortcut, kind of like when we converted to polar, a lot of times things were much easier. And oftentimes we'll use Green's theorem and also polar as well. All right, so let's take a look at another example, a second example. So we're going to evaluate the line integral over C. We're going to have y squared dx plus 3xy dy where C is the boundary of the semiannular region D in the upper half plane. that lies between the circles x squared plus y squared equal to 1 and x squared plus y squared equal to 4 with counterclockwise orientation. Right. So one thing I want to point out, the counterclockwise orientation that Green's theorem has stated is you have to have an orientation, but it's not a deal breaker if the orientation is clockwise, because you can just take out a minus, and then if the orientation was clockwise, you could just make it a minus c and then put a minus out in front and then use Green's theorem, because then minus c would have counterclockwise orientation. So we can still use Green's theorem when we have a clockwise orientation. We just have to take out a minus. All right, so let's first of all graph the region. And so we're going to have a region that looks like this. And so this is our region. Here, if this was on the x-axis here, this would be like at 1, and this would be at 2. And then here you'd be at -1 and -2 along the x-axis. And then your orientation along it is counterclockwise. So if we were doing this the regular way, we'd have a lot of line integrals to evaluate. So we have 1, 2, 3, 4 parts. So we'd have to do 4 separate line integral on the 4 different segments and then add those up. So that's going to be a real pain in the neck. But we're going to see that when we use Green's theorem, this problem is going to be kind of a piece of cake for us. All right, so the first thing we're going to do is we're going to look at the line integral over C of y squared dx plus 3xy dy. And so this is going to be your P and this is your Q. All right, so when you use Green's theorem, you're going to get the double integral over R. We're going to have qx minus py. So what would qx be here? Qx would be 3y. So we'd have 3y minus qx minus py. So py is 2y. So that's your qx minus py. And then this is dA. And of course, we can simplify this to just be y. Over R. So now what do we want to do from here? This is, you're back in chapter 15 and you're integrating over this region. How would you work it in chapter 15?
Using polar.
For sure, using polar. So we're going to use polar. So in polar, what is the y in polar?
R sine theta.
R sine theta. And what does dA become when we change to polar?
R dr d theta.
So we're going to have an R dr d theta. And then remember, we're sweeping out our region like this. We're going to be like this. With these angled segments. And so the R is going to go from what?
1 to 2.
1 to 2. And how about theta?
0 to pi.
0 to pi. So it's not all the way around. It's just 0 to pi, that's right. So we're going to go 0 to pi. All right, so now we're integrating 0 to pi, and then 1 to 2, and then we have r squared sine theta. And since we have a function of r times the function of theta, and we're integrating over a rectangle, we can write this as a product. So we can write this as the integral from 1 to 2 of r squared dr times the integral from 0 to pi of sine theta d theta. And now let's go ahead and evaluate that. So we're going to have 1/3 r cubed from 1 to 2. And this is going to be multiplied. We're going to have -1 times cosine of theta from 0 to pi. And so we're going to have 1/3 of 8 minus 1 times a -1 times -1 minus 1. And so this is going to give me 7/3 times 2. And so we get 14/3. And again, this problem is just going to be a real pain in the neck to do without Green's theorem. And you'd have to integrate over each of the segments. But with Green's theorem, it was kind of pretty straightforward problem to do. And so you can think of the Green's theorem as like that. It's like a nice shortcut. The one thing to keep in mind is that it has to be a closed curve. So you can't do it unless it's a closed curve. Now, could we also have used the fundamental theorem for line integrals to evaluate this problem? Well, we could if this was a conservative vector field. Is it a conservative vector field? If it's a conservative vector field, if you recall from the video that I sent you guys yesterday, then this quantity, the qx minus py, or the curl, is always going to be equal to 0. And for a conservative vector field, remember that the line integral of a conservative vector field around any closed curve will always be 0, because this curl part here is going to be 0. And so it's not a conservative vector field. If it had been, then this line integral would have been equal to 0. So we could not use the fundamental theorem for line integrals. That's only going to be a useful tool when we're integrating a line integral with a conservative vector field. All right, let's take a look at another example here. So we're going to find the work done by a force field and then we're going to have e to the x minus y cubed, and then cosine of y plus x cubed on a particle that travels around the unit circle x squared plus y squared equals 1 in the counterclockwise direction. All right, so okay, so we have our curve here. And this contains a region. Now, one thing I want to point out before I get started on this, you may wonder, can you use Green's theorem when you have a vector field in space, so you have 3 component functions? And the answer is no. There's another higher dimensional version of Green's theorem called Stokes' theorem that we're going to be looking at the end of the class. And we use Stokes' theorem to convert a line integral in space into something called a surface integral that we'll talk about later, a particular type of surface integral. And so that's going to be something really cool that we'll be looking at later on. That's sort of like a higher dimensional version of Green's theorem. All right, so going back to this problem here. So we've got the work is going to be equal to the integral over C of, here you have a picture of C there, of F dot dr. And in this case, we can write this in the differential form. So in differential form, what does this look like in differential form? So we're going to have this guy times, so we'll have e to the x minus y cubed times dx plus what?
Cosine y plus x cubed.
So we have cosine y plus x cubed times dy, times dy. So it's straightforward to put a line integral in this form into the differential form. Just the component functions, the first component, the x component is times your dx, and the y component function is times your dy. All right, so now we could parameterize this and evaluate this directly. It is just one curve, so we don't have to break it up. But I think we're going to see that it's still going to be much easier to use Green's theorem. So this is going to be your P, and this is your Q. So if we change this to Green's theorem, remember that we're going to have the QX minus PY dA. And so QX would be what? QX is
3x cubed squared, I mean.
3x squared. And minus PY, what's PY?
Negative 3y squared.
Minus 3y squared. And so this is going to be a double negative. And so it's going to end up being just 3 times the double integral of x squared plus y squared dA over r. And so now what?
Convert to polar?
For sure polar. We've got this circle and x squared plus y squared is screaming polar at you. And so we're going to have 3. The x squared plus y squared is r squared. The dA is r dr d theta. And it's a unit circle. So r goes from 0 to 1. And theta goes from 0 to 2 pi. And so this one is easy to split up as a product. So we're going to have 3 times the integral from 0 to 2 pi of 1 d theta times the integral from 0 to 1 of just r cubed. And so we're going to have 3 times 2 pi. This is going to give me 1/4 r to the 4th from 0 to 1. And so I'll have 6 pi times 1/4 of 1 minus 0. And so that gives me 3 pi over 2. And so kind of a pretty straightforward problem. Now, even though it's doable, if we try and do this by parameterizing the curve, then we're going to use r of t equal to cosine t sine t. And we're going to let t go from 0 to 2 pi inclusive. And then your line integral is going to look like this. So then your work is going to be the integral from 0 to 2 pi. And then we're going to have e to the cosine t minus sine cubed times a negative sine t. And then plus, you're going to have cosine of sine of t plus cosine cubed times cosine t all dt. Ooh. And so we have all that to integrate. So I'm not going to do it, but you can see it's going to be kind of a bear. It's definitely doable. But the Green's theorem was like a piece of cake. This one, we're going to have to be integrating like sine to the 4th plus cosine to the 4th. And some other ones that are just going to be like a u substitution, pretty straightforward. But the sine to the 4th plus cosine to the 4th is going to be kind of a pretty tough one. So Green's theorem, much easier. Questions on this so far? All right, the other cool thing about Green's theorem is that we can use it to calculate areas of regions in the plane. And so let me show you about that. So this is area in Green's theorem. Okay, so let's suppose C is a closed curve containing R. That satisfies all of the hypotheses of Green's theorem. Then if we look at this integral, so we're basically this is basically the work that the circulation vector field would do around this closed curve, half of that work. And if we apply Green's theorem to this, this would be equal to 1/2. Remember, this is your P and this is your Q. So we'd have the double integral. We'd have QX, which is 1, minus PY, which is a -1, over R. And then this is going to be equal to 1/2 the integral of 2 and this is equal to just the integral of 1 dA. And remember, this is equal to the area of R. And so we have, this is your C, and this is R, and we can use this to find the area of the region. And so we actually have 3 different area formulas. So we can use the one that we just used with the circulation vector field. So we can use any of those formulas will work. And this is where you have just any curve C that contains the region R, and that's going to give you the area of the region in the plane. All right, so let's take a look at an example. So we're going to use Green's theorem to find the area and so we've got this ellipse here. And then maybe here you've got the point, this is A0, and down here you have minus A0. Up here you've got 0B, and down here you have 0, -B, like that. And we want to find the area of that. All right, so what we have is that the area is going to be equal to 1/2 this line integral over C. And so we have to have a counterclockwise rotation around that. And then we're going to have minus y dx plus x dy. Now, in order to carry out this line integral, we're going to have to find some kind of a parameterization for this ellipse. So what we can do is we can use x is equal to a cosine t, and then y is equal to b sine t. And then we're going to let t go from 0 to 2 pi. So in this case, you're going to have the dx is going to be minus a sine of t dt, and then the dy would be equal to b cosine t dt. Right? So if I look at my line integral, then this is going to be equal to 1/2. I'm going to have the integral from 0 to 2 pi. And then I'm going to have the minus y is going to be equal to minus b sine t. And then the dx is going to be minus a sine t. And then the x is equal to a cosine t. And then the dy is equal to b cosine t. And then I have the dt. I kind of ran out of room for the dt there, sorry. So the dt is at the end there. All right, so from this first part, you're going to get a double negative. So it's negative b times negative a is going to be positive ab. And then here you're going to get positive ab also, so we can take that out. So we're going to have ab, and then we'll have the integral from 0 to 2 pi. We're going to have sine squared plus cosine squared. And so we end up, and I forgot the 2 there, so over 2. And so then this is going to be equal to AB over 2, and then we'll have the integral from 0 to 2 pi of just 1. And so what we get there is we're going to have AB over 2 times 2 pi. And so we have AB times pi. So if the a and b were the same, so it's a circle, then you'd have pi a squared or pi r squared, which is the area of the circle. And so that's it. So that's our area. Now, if we had to do this just using a double integral, so with a double integral, we'd have to evaluate this. So we'd have the double integral, we'd have minus b over a, and then the square root of a squared minus x squared. And we'd have b over a so we would have to integrate like that. And so the line integral is going to be much more straightforward than having to do it with a double integral. Questions on that? All right, so let's move on to something else. So when I stated Green's theorem right at the beginning, it said let R be a simply connected plane region with no holes. But actually, Green's theorem can be extended to regions with holes. And so what I want to do is I want to show you a way to extend Green's theorem to a region that does have holes. Okay, so what we're going to do is we're going to take a look at a region that has a hole in it. So we're going to let R be a multiply connected region whose outside boundary curve C1 is traversed in the counterclockwise direction and the inside boundary curve C2 is traversed in the clockwise direction. So R is always on the left. And so let me draw a picture of what this could look like. So maybe we have a region like this, and then here you have a hole in it. And then you have your C2 here. So your C2 has clockwise orientation like that. And then your C1 has counterclockwise orientation like that. And so as you go around the boundary, if you were like in a car on the boundary, you would look out on the left side, the driver would look out his window and he would always see the region R there. And then if you were on the outside boundary curve, again, you'd look out your left window and you'd still see R. So we're going to divide R into two simply connected regions, R1 and R2, by making cuts. And so if we look at, let's redraw this picture here again. And so we've got this hole here. And then, so we're going to make these cuts here. And so we're going to have L1 is going in this direction. And then if we use another color here, we're going to have minus L1 is going in this direction. And here you're going to have L2. And then if we look over here, that's going to be minus L2. And then we're still going to have, this is going to be C. And then the orientation around this one is going to be, we call this C1, and this is C2. All right, so then we're dividing this up. So we have R1 now, and then R2. And if you look at R1, R1 actually doesn't have a hole in it. So we don't have a hole in the boundary. So R1 and R2 are simply connected regions. And so for that reason, we can apply Green's theorem. So then if we look at and so we're going to have, if we look at the double integral over R, and then we have the qx minus py dA, we can write this as the double integral over R1 of qx minus py dA plus the double integral over R2 of qx minus py dA. And so this is going to be equal to the line integral of p dx plus q dy over the boundary of R1 plus the line integral of p dx plus q dy over the boundary of R2. And so, like for example, the boundary of R1, we would have this top part of C1 followed by L1, followed by this top part of C2, followed by L2. The boundary of R2 is going to be this lower part of C2, and then negative L2, the lower part of C2, negative L1, and there you have it. Now, remember on these segments, we can write this as the union of all those parts and the union of all the parts that make up the boundary of R2. And the parts along the opposite orientation cuts cancel out. So then this is just going to be equal to the line integral over C1 plus the line integral over C2 of p dx plus q dy after we cancel the opposite orientation cuts. Cancel. All right, so that's how we can do it. Let me check on the time here. All right, so we're going to take a look at one example where we do a calculation over a multiply connected region. And if we run out of time, I'll send you the recording for it, but I'm going to continue to do this next example till it's done. It may take a little bit past 12:30 to finish this one. Any questions on this so far? All right, so let's take a look at an example. So this is example 5. So we're going to evaluate line integral over c of minus y over x squared plus y squared dx plus x over x squared plus y squared dy, assuming c is a piecewise smooth simple closed curve with counterclockwise orientation such that when C does not enclose the origin, and 2, C does enclose the origin. All right, so let's first of all remember that if we're going to use Green's theorem, we need to calculate if this is P and then this is Q, we're going to need to calculate QX minus PY. So let's, first of all, let's start out by calculating QX and PY and see what they come out to be. So if Q is equal to X over X squared plus Y squared, then that means that QX, we're going to have to use the quotient rule. So we'll start that by squaring the bottom. And then we have the low times the derivative of the high is going to be X squared plus Y squared minus the high times the derivative of the low, which is 2X. And so what that's going to give me is I'm going to have Y squared minus X squared over X squared plus Y squared squared. So we have that. And so if we calculate the P is going to be equal to negative Y over X squared plus Y squared. So now let's calculate PY. So again, we're going to square the bottom, square the denominator. And then we have the low times the derivative of the high, which is going to be negative 1. Minus the high times the derivative of the low, which is 2y. And so in this case, we're going to have minus x squared and then plus y squared. So this is going to end up being y squared minus x squared over x squared plus y squared. All right, so if C doesn't enclose the origin, then both partials are continuous.
Professor,
Yes,
you forgot to square the bottom on PY.
yes, thank you.
Mhm.
All right, so and so in this case, we're going to have the integral along C of P dx plus Q dy is going to be equal to the double integral over R of Qx minus Py. Now you can see that they came out the same. So this is just going to be the double integral of 0 over R dA, which is equal to 0. So in the case when C does not enclose the origin, then we're going to be free to use Green's theorems, because one of the requirements is that our first partials have to be continuous on an open region containing R, and they would be. All right, so that's what we would get in this case. So now let's look at the case when C does enclose the origin. So this is case 2. So let's suppose all right, so in this case, we're not going to be able to apply Green's theorem directly. And so we're going to have to find a way to work this problem sort of indirectly. So we're going to let CA be a circle with center at 0, 0 of radius A contained in R with counterclockwise orientation. All right, so let me draw a picture of what I have here. So I've got a region here, and here you're going to have right there is 0, 0. And then your CA. So you're going to have the C has counterclockwise orientation. And remember that we've defined C of A to have counterclockwise orientation, but the inside curve needs to have, like what we talked about before, needs to have clockwise orientation. So we're going to look at minus CA. So if I look at minus CA, that's going to have clockwise orientation. And so then making cuts, we divide R into R1 and R2, which are simply connected regions. And so we're going to make a cut there and another cut there. Like that. And then we can talk about and so we're going to have this region up here is going to be R1. And here you have this region R2. And so to go around R1, you'd have this upper boundary curve followed by the first cut, maybe L1 here, and then this upper part up here. And then on this part, you'd have the other cut. So you'd have a counterclockwise orientation around R1, around the boundary of R1. Now, if we look at R2, we're going to have this lower boundary and then minus the L2 cut here. And then this lower part here. And then minus L1. And so you also see that you have a counterclockwise orientation around the boundary of R2. And so what we can do is we can apply Green's theorem on those boundaries. So then if we look at the double integral over R1 of Qx minus Py dA, then in this case, the R1 region doesn't include the origin because the origin is right here. And so we can apply Green's theorem and we can see that this is just going to be equal to 0. And our partials are going to be continuous on this region because it doesn't include that place where they're undefined. And so this is just going to be equal to 0. And then also the double integral over R2 of Qx minus Py is again 0. And so the whole sum is equal to 0. And so what we can do is on each one of these, now we're going to use Green's theorem. So by Green's theorem, this is just going to be equal to the integral of the boundary, like what we talked about before, of P dx plus Q dy over C plus the integral of minus CA P dx plus Q dy, the inside boundary. So what I'm doing is I'm using what we talked about before. So remember before, it just became the boundary curve. So when we have this in our two regions, it just became around the outside boundary plus the integral of the inside boundary, the one that had the clockwise orientation. That's what it comes down to. So in this case, in this particular example, we have the C, which is the outside boundary, and then minus CA is the inside boundary having clockwise orientation. All right, so we have that. And so now what this means is that this is the same thing as saying the integral of C of P dx plus Q dy minus the integral, and here we have CA of P dx plus Q dy, and this is equal to 0. And so what that means is that our integral is equal to the integral around C of A. And so we just need to calculate this one. And so what we can do is we can let x equal a cosine t, y equals a sine t, and then 0 is less than or equal to t is less than or equal to 2 pi. And remember that your p is this guy and your q is that guy. So we're going to substitute in for that. So in this case, if we write out what this is, so we're going to have this integral CA. Let me go ahead and write those in. So we're going to have minus y over x squared plus y squared dx. And then plus, we'll have the x over x squared plus y squared dy. So we have those guys. So let's plug in now. So we're going to have the integral from 0 to 2 pi minus y. So we're going to have minus a sine t. And then dx is going to be minus a sine t. And then this is going to be over a squared cosine squared t plus a squared sine squared t, which is just a squared. And then for the other one, we're going to have x, which is a cosine t. And then the dy is going to be also a cosine t. And this is going to be over the same thing. So we're going to have the a squared cosine squared of t plus a squared sine squared t. And all of that is dt. And so this denominator is just going to be a squared. So we're going to have a squared over a squared. And then we'll have the integral from 0 to 2 pi of just sine squared plus cosine squared t. And so we have just the integral from 0 to 2 pi of just 1, which is equal to 2 pi. So you see we get a different answer. So we get a different answer of 2 pi. All right, so I want to do one more thing before I end today. So before we talked about the conservative test. And so now that we have Green's theorem, we have everything we need now to justify the conservative test, along with what I showed you last time. So let's go ahead and do that just to wrap things up on that end. So there's a theorem. This is the conservative test. Now, we're not going to be able to justify the conservative test in space because we would need a higher dimensional version to justify that. So later on, if we have time when we do Stokes theorem, I'll show you why the conservative test works in space using Stokes theorem. All right, so let's suppose F is equal to PQ is a vector field. Over an open simply connected region D. And we're going to suppose also that P and Q have continuous first partials on D. So we can use Green's theorem, what this is setting up for. Then if Qx is equal to Py on D, F is a conservative vector field. I think previously we used M and N. So remember it was My equals Nx. So this is meaning the same thing. The P is the first component. The M was the second component, the first component before. So it's the same thing as saying My is equal to Nx. All right, so let's do a proof here. So let's let C be a simple closed path in D. And R the region enclosed by C. Then if we look at this integral of F dot dr over C, this is the same thing as in differential form, the P dx plus Q dy. And by Green's theorem, this is going to be equal to the double integral over R of Qx minus Py. And remember, we're assuming here that Qx is equal to Py. So that means that Qx minus Py is 0. So this is equal to the double integral of 0. And this is equal to 0. Now, suppose C is a closed path, but not simple. So maybe your path is looking like this. And so this is C. And you can think of C as being the union of C1, C2, C3, C4. Maybe we keep on going like that till we have Cn. This is Cn minus 1 here, one right before it. Where those are simple closed paths. So if we look at the integral over C of f dot dr, this is equal to the integral of f dot dr over C1 plus the integral over C2 of f dot dr plus the integral over Cn of f dot dr. And each of those would be equal to 0 by the above. So this is equal to 0 plus 0 plus 0 equal to 0 by the above. So just to wrap this up, hence if C is any path in D, then any closed path in D, then the line integral along C of f dot dr is equal to 0. And so this is equivalent to this line integral of C of f dot dr is independent of path. By theorem 3. Independent of, path, which is equivalent to F is a conservative vector field by theorem 4. From the last class or the lecture. And that's it. So, so basically what it boils down to is that around any closed curve, if the qx is equal to py, then around any closed curve, when you apply Green's theorem, you're just integrating 0. And so when you have the integral, this line integral of C around any closed curve in D is equal to 0, then that's equivalent to that theorem 3 by the independence of path, and then by theorem 4, independence of path under those conditions that we have here is equivalent to the vector field being conservative. And that's why the conservative test works. All right, that's it for today. So next time we're going to start in with surface integrals, and we're going to be working on that through the rest of the week. We'll be looking at surface integrals and parametric surfaces. And then also, along with that, we're going to be looking at flux integrals. See you next time.